Every year, China's southeastern coast braces for impact. Super typhoons, massive atmospheric beasts, packing winds over 150 miles per hour, rip through the East China Sea, turning high-altitude construction into an engineering nightmare. While the wind attacks from above, the ground offers no stability. Shanghai is built on a river delta of soft, waterlogged clay. For a mega-tall skyscraper, the location is a geological contradiction. Building a 2,000-foot tower here, using traditional, rigid structural methods, was considered a mathematical impossibility. A standard design would either sink under its own weight or snap like a twig under the pressure of the wind shear. Despite these risks, a 1993 master plan called for 3 super-tall skyscrapers to rise in Pudong, representing the past, present, and future of the nation. The Jinmao and the World Financial Center were the first to arrive. The final piece, the future, was designed as an asymmetric, twisting dragon. It was a fluid architectural vision that symbolized a country on the move, reaching toward the heavens. For engineers, attempting to stabilize the tower's massive weight here was the equivalent of balancing a refrigerator on a wet sponge. To keep the tower standing in Pudong's soft mud, engineers could no longer fight nature with brute force. They had to outsmart it. To prevent the tower from sinking, engineers had to reach stable bearing layers deep beneath the silt. They drove 980 steel-reinforced concrete piles 283 feet straight down into the mud. A fleet of 400 trucks delivered 60,000 cubic meters of concrete in a 63-hour continuous operation to create the base pad. At the time, it was the largest pour of its kind in history. By 2012, as the structure grew, the sheer mass of the tower began compressing the soft earth. Large cracks appeared in the surrounding streets, threatening nearby buildings and underground subway lines. The team responded by pumping specialized grouting directly into the soil. This stabilized the perimeter and halted the settlement, preventing a collapse of the local infrastructure. With the foundation secured, the engineering challenge shifted upward. As the tower climbed into the sky, it entered the path of the region's most persistent threat, the wind. Above 1,000 feet, the primary structural concern is no longer gravity. It is the extreme force of high-altitude winds. This graphic shows what happens when high-speed air hits a flat-faced skyscraper. The airflow separates and forms swirling eddies on the sides, an aerodynamic phenomenon known as vortex shedding. These swirling vortices create intense, alternating suction forces. During a super typhoon, this organizes into a rhythm that shakes a tall building from side to side, generating enough force to snap a traditional structure in half. To find a solution, the design team tested dozens of scale models in a wind tunnel. They searched for a geometry that would prevent these wind forces from ever organizing. The data revealed a precise mathematical solution, a structure that tapers by 55% as it rises, with an exact 120-degree twist. As wind strikes the spiral, it breaks into disorganized disturbances that cannot lock into a destructive rhythm. This geometry reduced wind loads on the building by 24%. It was an economic miracle, allowing the team to eliminate 20,000 metric tons of structural steel and cut $58 million directly from the construction budget. The tower's skeleton relies on a central concrete core and 12 massive supercolumns. These are tied together by outrigger trusses, giant steel belts that act like heavy-duty shock absorbers to keep the building from snapping in a typhoon. But the most radical innovation is the double-skin facade. An inner glass cylinder houses the office spaces, while a second, twisting glass skin takes the beating from the weather. This buffer zone acts like a giant thermos, slashing energy costs while creating public sky gardens in the clouds. Building that outer skin required over 20,000 uniquely shaped, computer-tracked glass panels. Construction workers installed these thousands of feet in the air while facing extreme heat and high-altitude winter winds. Supporting this glass exterior is a 98-foot wide concrete megacore. Massive steel outrigger trusses connect this central spine to supercolumns on the perimeter. This structural web acts like the outstretched arms of a tightrope walker. It distributes forces across the entire frame, allowing the building to absorb the shock of direct typhoon strikes and magnitude 9.0 earthquakes. Even with an aerodynamic shape, A 2,000-foot tower will still sway in heavy winds. This motion can be enough to cause severe seasickness for the people on the upper floors. To access these floors, Mitsubishi designed aerodynamic elevators that travel at 45 miles per hour. The cabins are mechanically pressurized to prevent eardrums from bursting during rapid ascent. At the top of the tower sits the building's final defense, a 1,000-ton copper pendulum known as a tuned mass damper. When wind pushes the tower one direction, this immense weight swims the opposite way. This movement cancels out kinetic energy, stabilizing the structure. This system uses magnets to slow the weight frictionlessly. Unlike traditional shock absorbers, this eddy current damper responds silently without any parts touching. The damper acts as the building's brain, constantly adjusting to movements to ensure human comfort, even during the most severe coastal storms. The tower topped out in 2013, with the final budget reaching $2.4 billion. This investment supported the integration of high-efficiency infrastructure designed to reduce the building's environmental footprint. The double-skin facade reduces energy usage for heating and cooling, while the plumbing system harvests rainwater. At the peak, 270 wind turbines generate 350,000 kilowatt-hours of electricity every year. This system captures kinetic energy from the same storm winds that once threatened the building's stability, turning a structural load into a localized power source. These innovations earned the tower a LEED Platinum certification, the highest green building rating on the planet. By turning the wind's energy into an asset, engineers didn't just build a skyscraper, they discovered a smarter way to exist within nature. The result is a structure that doesn't just survive the hurricane, it harmonizes with it.